Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about radio encoding technology part 2. So we're going to focus on QAM on OFDM. So let's dive deep into it. Now you have to understand that the last part we talked about just radio as in like analog domain. But current world right now is digital, and not to mention it's also very wireless. So both of these puppies, radio waves and digital signals, have to make love to each other. So we need clever way of packing it. For example, when we did early packaging of signals into radio waves, we were dealing with basically pager network. Now it's not the same. Not only a lot of people, far more, exponentially far more people have devices on themselves. So customer base has grown exponentially. Each customer demands much higher. Like this puppy was like kilobits per second, and that's being optimistic. And now we need megabytes per second. So fundamentally, we need a clever way of packing radio signal for our modern world to work. Because be mindful, wavelengths have a limitation, because you do not want a scenario where it's like, hey, somebody is using a Wi-Fi and basically airport's Doppler radar malfunctions because of it, or like, miscalculate something, because again, they are on the same spectrum. You do not want that. So fundamentally, spectrums are locked. It's like, hey, you only have this much room, this much wiggle room, do the best you can do. And from a radio point of view, this is like, you might like, okay, this is human law, fair enough. But from an engineering point of view, physics domain point of view, each wavelength has a certain type of signature to it. For example, 5 gigahertz, the 5 gigahertz radio you have on your Wi-Fi, while it does have higher bandwidth, it does not have high transmission. 2.5 gigahertz have much further transmission. Same radio, same power outage output, it will always be different. And again, you can go the other way. You will like, okay, what if I just want to maintain a connection, basic enough WhatsApp or something like that? Go to sub gigahertz radio, as in below 1 gigahertz. This puppy will work underground metro. You can still receive your Wi-Fi signal. Yes, there it's called Wi-Fi Max. Very low bandwidth, like very low, like few bytes per second. But again, if you are talking about Internet of Things, or just like maintaining a IoT device connection, or just like something like basic ping, more than good enough. So there is a reasonable reality where you want to be very optimistic and optimized with your frequency, not only for human law but also for engineering reason. And physical bandwidth that is available is limited, because every time you are changing a radio frequency, you're going dinkichika into that, it is creating harmonics, and those harmonics are destroying other things. So if you have, let's say, this tower has to communicate to 10,000 mobile phones. If one mobile phone signal starts to create harmonics in other bands, it will interfere with those, and they will start to increase their signal output, and then more. Turns out they're supposed to be able to talk to let's say 10,000 people, will barely able to deal with 1,000. That's why harmonics also matter, and that's another aspect, like how much band buffer you have. All of those things play into it. It's not like, let that be very clear, I'm not saying it's just law. There is a reason for that law. Like physical law is below it, so to say. So utilizing wisely is primary requirement, and high speed cannot be done if you are sloppy with it. Like physics will not allow you to do that. And analog to digital, that's how we started. It was way too inefficient. It got the ball rolling, but it was too efficient. Heck, it was too efficient for Wi-Fi. So let's dive deep into it. Now, early technology is basically, we started with the ancient era. Before we had AM or FM, it's a continuous wave spark gap. Basically, we had T, 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 basically very old school screaming. Morse code. Morse code is digital, fundamentally digital. That's how we started. And then we went to amplitude shift keying, ASK. This puppy was very short-lived, because the idea was, what if we had loud signal for, let's say, 1 and small signal for, 0. Problem is amplitude changes a lot by natural interference, degradation, and all of that. So this became very unreliable. And I'm talking like 1920 people are like, yep, this is BS, thou shall give up. Then we went into frequency shift keying. Frequency shift keying is a bit slower. Like again, when I say slower, I do not mean compared to AM. I mean slower compared to what we use today. But it was robust, as in natural interference. While your amplitude will go up or down, it will not change the frequency. The primary carrier frequency will remain intact. So if you're changing the frequency itself, signal in that change will remain intact. And that's how we started with frequency shift keying. Robust puppy. And yes, your FM radio that we use for marketing and all that, it has a digital channel using almost the same encoding methodology inside that FM transmission. If you have a recent car radio, it can show like, channel this, song title, name and all that. Although I do not know what happened to FM now, because many modern phones don't have radio, so I do not know what's happening nowadays. But again, it's slow but robust. Then we had binary phase shift keying. Now this puppy is like, hey, frequency still has some wiggle room, some clarity issues are still there. What if you did the mathematics on phase shifting? I have already covered this last video. It's just that your signal, if it looks like a W, it's going from 1 to 0. If it looks like a M, it's going from 0 to 1. So there is no what you call doubt, clarity, crisp clarity. So this is core right now, meaning if your mobile phone is receiving GPS, it is receiving that same protocol, encoding, so to say, BPSK, because this was utilized for GPS. This puppy is robust, like robust, as in Voyager. That's how we are talking to Voyager. This puppy, like even a very small amplitude signal, it will have almost like it screams, I'm going from 0 to 1 or 1 to 0. So it's very crisp. So, and military communications also utilize that. Now, does that mean you can have a software-defined radio and receive the signal? Yes. Does that mean you can decode it? Half, yes. As in, you will get the binary bit. You can't do anything with that because that's scrambled. That's the whole point of encryption. You can receive it, you can decode it, but you will still get a scrambled egg. And whenever you needed basically something that can punch through atmosphere, this puppy was your guy, so to say. Very robust, very strong, clear. Basically, it's not signal to noise ratio. It's more about like, can I trust that 0 to 1 happened or 1 to 0 happened or not? This puppy has like highest clarity, where it's like, no, it happened. You got a W, you got a M, it's clear. But again, bit rate wise is very slow, because then how can it work for GPS? GPS is nothing. It's a time clock going ting, ting, ting. It's very simple. Like it's just ting, 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 nothing more. So it does work. Like we started our journey into digital era with these puppies, but we needed something more, mathematically more. Then we introduced the QAM mathematics. So math started on this in 1960. And the idea is, what if you have a one wave? Okay, cool. But that's one dimension, right? Like whatever you do, it's still one domain. Somebody's like, nah, man, what if we put two domain data into that one signal? Amplitude over time, what if we put two signals on that? You're like, how? Well, imagine your Wi-Fi radio. You take 5 gigahertz from it, okay? Cool. You take the 5 gigahertz, that's what we classify as carrier signal. You take it, you split that puppy up. You take one raw, you do amplitude modulation on that. Then second, you shift it. Now, like how the heck you shift a radio signal? If you study electronics, you know this is what job of a either capacitor or an inductor. Depending on your design, depending on your choice, you could choose capacitor, inductor, or mix of both. So you will achieve the right tuning. The idea is you do not want to shift 180 degree. You have to shift only 90 degree. You shift it. Now you have two basically frequency. Be mindful, they are in the same what you call domain. They are still 5 gigahertz. They are not changing like 5.1 gigahertz or 5.2 gigahertz. They are same 5 gigahertz. It's just that you have two of them, and we call it Q and I. So real number and imaginary number, and then you change it. You tweak it. Once you tweak it, then you merge them into an antenna, and then it screams into the void. Now, like, wait a minute. If we mix these two puppies, that will create a complex wave. Yes, it does. And that complex waves is emitted from the antenna. So that's why I said like single amplitude over time. You're not emitting two wavelengths. You are emitting combination of these things. Now, because you are emitting combination of these two data, which has been independently tampered with, you can reconstruct the two data stream. Basically, I and Q can be reconstructed. All you have to do, same thing in reverse. Receives the carrier signal, split it, shift one of them 90 degrees, and voila, you have Q and I signal. Now, that is not that difficult. We figured it out surprisingly early on. Now the question becomes, okay, how do you transmit data? Like this is when I used to work with basically satellite radio. You can do that, like buy a very cheap SDR radio. If Russian Meteor satellite is still active, it should be able to work. It does send this quadrature data. So the idea is you have I and Q. So every pulse, every symbol sends a coordinate data. So coordinate could be here, 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 here. Now that coordinate is still transmitting one pulse. It's like tada. So where it is falling on the coordinate map, that describes the data. For example, if it falls here, it's 0, 0. If it falls here, it's 0, 1. It falls here, it's 1, 1. It falls here, it's 0, 0. So that's how you map it. So every signal you are getting, you are taking the signal, putting in a coordinate map, getting the bit out. Now like, okay, what if we make this 4 quadrant more? What if we make it like this? So you have, oh, if it falls here, it's 0, 1, 0, 1. If it falls here, it's 0, 0, 0, 0. If it falls somewhere else, it becomes something else, like, 1, 1, 0, 1. And that's how you increase the bit depth, by increasing the coordinate map. Now, you must understand that to do this, your signal quality has to improve. Basically, the transmitter must have a very clear distinct step between I, basically 0 I and 100% I. It must have clear slices, like tuck, 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 clear slice. And then for Q also same, tuck, 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 clear slice. Only then you will have this sort of map. And a receiver, like in this design, it's receiving 4 bit of data. So it's not like 4 pulses, it's 1 symbol. You take that symbol, put it in a coordinate map, bam, 4 data. Basically imagine Martian. Like Martian had only 1 domain data. It's like, where that is looking. That's it. It's the same thing. Only it's 2. So you had where I'm looking, how far I'm looking. So, where, come on, yeah, where, far, near, where, far, near. So 2D data. That's the whole point. I and Q. And you're like, okay, but I and Q traces out a circle in many animation you see in the, yeah, because the amplitude is always kept same. You have to change the amplitude. Basically, I amplitude has to change and Q amplitude has to change. Then you can map it perfectly. And the highest coordinate map right now in use is 4096. Yes, there will be 4000 points there. How much bit is that? One symbol is 12 bit. Tick, 12 bit sent. It's literally sending more than 1 byte. Literally in one set. Done, sir. Basically, 2 of those symbols will translate into 3 bytes of data, complete bytes. That's why you are achieving like, 1 Gbps sort of speed. Penalty, because these signals are so, the modulations are so minute into them that it does require almost looking at the Wi-Fi antenna. Like it has to be line of sight direct, meaning ranges are like freaking 3 meters. So if your Wi-Fi goes further than that, the calculations matrix will be like, yeah, signal not stable enough, drop it to, let's say, 4096 to 1024. 1024 should be able to work in your house, inside a room at least. And then if it goes any further, 512. Goes any further, 256. 256 should work anywhere, so to say. So basically this is QAM. And again, that's why the satellite was using only this. Can modern satellite use that? Of course they can. It's just that, do you really want to take a risk against a cloud, or do you want to punch through the cloud? So you want to punch through the cloud, you want to have clear signal. If you are like, hey, it's a short range, you generally can go YOLO, like 4096 YOLO. So be mindful, single data, single signal made into 2 signals, 2 amplitude changes emitted as 1 amplitude over time, utilizing the magic of mathematics, made a 2D vector map. In that 2D vector map, you are spotting where the signal is and comparing it to lookup table. It's literally a lookup table, and voila. How many symbols? Depend on the design. Some symbols are dual symbols, as in like 00, 01 or something like that. This is 4, and you can go as high as 12 bits. So this is QAM. This is foundation of every digital radio. Then we come to OFDM. Now OFDM puppy is like counter to reality, as in reality says, oh, you want to send so much frequency, we can't send it, right? Because again, signal degrades too quickly, noise overlaps everything, we have to reduce the symbol map. And then like, okay, what if I increase the frequency, increase the baud rate? Whenever you are hearing the word baud rate, it generally means the physical change, basically how quickly it's changing. Yes, it literally does this. So if you want to increase the baud rate, physics fights back. Physics is like your mobile phone, your tower, you send signal, tada! So path A is signal. But here's the deal. You are not living in a world where radio is traveling via optical fiber. It is omnidirectional. You're going boing, this is going boing. So it is bouncing from everywhere, meaning buildings, other buildings, stuff like that. So if you are switching way too fast, when your antenna is receiving it, path 1, path 2, path 3, they are so minutely, apart from each other, they are interfering constructively or destructively. Basically, they are destroying the symbol, which we call inter-symbol interference. The data packet itself is getting destroyed because of the data packet, meaning one data packet arrived, another data packet, bam. If you are optical fiber familiar, you know optical fiber also has this, what we call multimodal or single modal. So because 5G is not, or any advanced radio is not dealing in single mode, it has to compensate for multi-mode transmission issue. So how the heck you do that? Well, only physical solution is slow it down. You can't have like, you have to slow it down. So this becomes big enough that overlap causes minor issue. So we do that. Okay, it becomes highly immune, but penalty is slow. Okay, how do we compensate for it? You can't increase, you're like, okay, that's one channel, but we can't increase the QAM map. So how do we do that? Well, make millions of channels. So the idea is you take the serial data that is coming from your mobile phone, let's say SoC, and then you create a multiple digital parallel streams. How many streams? Depends on you. It could be 50 to 3000. So you take that many streams and then you apply a magic. Now here's the deal. That stream mathematics you did, they are getting encoded into radio waves, but not on a hardware level. This is happening like this, like the colors of a white light. Basically, you are doing that on a mathematical domain, which we call Fourier transform, fast Fourier transform. You are mathematically doing, it's like, what if I have to send 3000 channels of data, 3000 channels, each channel should have two domains of data, I and Q that we have already talked about, symbols, you are basically sending symbols, but it's just that each is slow. Like each channel is slow, but you are sending so many channels, you are parallelizing it and the speed is very high. So each channel is slow, cool, awesome, but you can send still, you can send, let's say 256-bit. So that should transfer like almost, let's say 4-bit of data. Let's just say you're sending 4-bit data, one here, 4-bit, 4-bit, your mobile phone is giving you hundreds of bits. So like 4-bit, 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 you're doing that. You are doing it in mathematical domain. Basically, for fast Fourier transform, you're doing it. And then you are transmitting it over prism, or basically your radio antenna. It becomes one signal. That one signal your mobile phone receives, mobile tower receives, and it can easily decode it. Why it can decode it? Because it was not getting destroyed by inter-symbol interference. How it can decode everything that you mix together? Exactly as we did in school. You send it through a prism. Exactly you do it in basically optical fiber. You have white light coming in and it spreads out. Now what is light? Frequency, wavelength. What is radio? Wavelength. So somebody figured out this is mathematics and we do it fast Fourier transform. So why do this have like 3000 channels, or like channels are so close together? Why? Well, here's the deal. If you do frequency duplex modulation, each frequency will take very large space. If you have so much large space, the bandwidth becomes compromised, meaning a mobile tower is like, bro, I can only deal with 100. So that's not acceptable. So we do orthogonal. What does orthogonal mean? This is black magic of mathematics, which means non-interfering. Each channel is not interfering with the other channel, meaning every channel, if you are focusing on it, basically it's a prism is focusing on it, it can recreate it without any issue. It's like, I got you. This is the exact frequency you have, I got you. Like in how we optical fiber, you can send a red laser and blue laser and both can be completely interference free from each other. That's the same thing is happening in radio. That's what basically orthogonal frequency is. Basically one symbol apart, apparently. It's not wavelength, it's not 180-degree apart, apparently. It does require a bit more complex mathematics, but that's what they're doing. And again, you do not have like 3000 antennas in your mobile phone. There is only one. It's just the mathematical silicon does that calculations, fast Fourier transform. If you have heard, like in the early days, like, iPhones were having hard times with 5G technology. They even got sued by Qualcomm or Intel, somebody, it had something like that. It's just that doing that mathematics in silicon, it's hard. So orthogonal frequency division, a multiplexing meter. Basically, we are compensating for the penalty. Penalty number one, you can't have 10,000 symbols in your signal, because again, interference will destroy it. Like just noise degradation will destroy it. Okay, you reduce it. So you can only transmit 4-bit. Okay, you can't send hundreds, 4 bits. Okay, one symbol is 4-bit, but what if I send very quickly? Again, inter-symbol interference will destroy you. So noise is limiting how much you can send on one pipe, and how fast you can send is being limited by physics. What if you have thousands of pipe? That's the only solution we have. This is what we call OFDM. This is the reality of everything. So any signal that you think about generally is this OFDM carrying QAM. Now generally QAMs, when you're talking about this sort of a mobile phone, they are generally 256 bits. Not bits, as in like 256 map, that coordinate map would be 256. Because again, you can have very high, it just will not be able to be legible. So mobiles have to work on very long range, so they are only 256. And even 256 generally they downclock to 128. So what can we expect in the future? Yes, we are touching the upper limit of basically radios. Again, we knew this because be mindful, the math that we are using is 1960, Fourier mathematics 1600. So there is an upper limit of radio because of harmonics, because of physical laws. You can't do too much about it. And we are reaching a point where we no longer want like maximum stupid number, we want reliable signal. So like again, 4G is supposed to have hundreds of megabytes per second, at least 100 without any issue. How many of you got that? 5G is supposed to be 1 Gbps. How many of you reliably can trust it? Like, hey, I'm mobile phone 1 Gbps. It's like once in a while, if nobody else is using on the network, then you can get it. Sometimes like the moment you go into any mild crowded area, it's like lol. So people are trying to do different mathematical domain. So current domain that people are working on is Doppler shift. So the idea is as you are moving along, as the signal is bouncing around, it has a Doppler shift into it because again, it took a longer path. So they're like, what if we use Doppler as a different domain? Like how we had I and Q, what if Doppler domain becomes another data point? And using that domain, we can reinforce the signal. So even weak signal that is bouncing everywhere, right now we are ignoring the bounce signal. In 6G mathematics, we should be able to reinforce it. Oh, you come from here. You basically are overlapping, stacking those signals, and it will become clear. And if you can do Doppler shift calculations properly, you should be able to basically become speed free. Meaning if you are in bullet train, it still should be 6 Gbps. So, or even a hypersonic plane. I'm not joking. They are literally saying that like 6G should work on hypersonic plane. And it will require AI calculations inside. Again, it's no longer on mathematical domain. Like it's fast Fourier transform. That's old age. We need AI, and I mean actual AI that is calculating basically it has to physically map your domain in 3D and in like how radio waves are scattering. Only then it can map the echo paths and optimize it. And theoretical target is 1 terabits per second or 125 gigabytes per second. So this is what we call stupid. Again, we don't want this. We don't need this. This is what we call stupid. What we need is actually basically the mathematical awareness, what we call spatial reality awareness. So you can handle lower grade signal with far more reliability. That is interesting. 6G won't be interesting because it will be faster. We never gets faster. So, but the fact that signal will be more robust, that I like. And the true innovation in radio would be what you call this puppy directly talking to satellite puppy. That is the final dream that I want to look into. If, knock on wood, if I live long enough, it should become reality. This is ATS Tower. They are a mobile service provider company, but they realize if they directly try to become a service provider, they'll go bankrupt because licensing, again, spectrum licensing, it's brutal. So they're like, okay, we're not going to do that. We're going to partner. Like in America, we're going to partner with Verizon. In India, we're going to partner with VI. So idea is, no matter where you are, if your phone can see the sky, you should get a signal. Again, early days, right now, it's like you should be able to get almost like small pings, maybe a WhatsApp message. But AST, if it is working and if it gets to what they are trying to do, you are looking at least 10 Mbps to 100 Mbps. Basically, you should be able to do a video call. If that happens, again, you only need like 10 to 20 Mbps to have decent experience on your mobile phone. So again, that's what I'm looking for. Like there is a place I travel to for like one of my factories of water production, bottled water, like, mineral water from basically, Himalayas. It's literally in Himalaya. So very poor signal there. So I'm like, please come there. Because again, we want Starlink there. It's just that Starlink, Indian government not making love properly. So this might happen because again, VI is an Indian company. So I'm hopeful with that. So this was my presentation on basically how the heck we transmit gigabytes of data over radio. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me a disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. As always, thanks for watching.